So, this says in 2.9 that we looked at a logarithmically scaled axis. We didn't. I took that part out, so it's a lie. I didn't take it out of here. So in a semi-log plot, one of the axes is logarithmically scaled. In AP Calculus, Pre-Calculus, we will only be scaling the vertical axis. It could be done with the x-axis as well, but we won't be looking at those types of problems. So here's an example right here. This is exponential data right here. And this is a regular, like just XY plot. You can call it the Cartesian plot is what they call it, like your just regular XY coordinate plane, right? And so you can see here, you always want to pay really close attention to your scale anytime you're looking at a graph, because a lot of times we'll assume it's like 1 and 1, but it's not. So my years are going up by 20 right here. My population is going up by millions, right? So I got 1, 2, 3, 4, 5 million here, and this is the population of English Americans in the current United States. And it's from 1620 to 1820. So you're looking at the number of, I guess, people of English descent that are in the U.S. over this time. So you can see right here, I definitely cannot tell the difference between these first few points. Like really all the way out to maybe like really even 100 do you start seeing, or you can sort of tell what's going on. So there is a benefit to looking at this on a semi-log plot. So what they have done, instead of going up 1 million, 2 million, 3 million, 4 million, 5 million, 6 million, 7 million, on our y-axis, they have 10 to the first power, which is just 10, right? And then 10 squared, which is 100. And this is 1,000. And this is 10,000, 100,000, a million, 10 million, right? So each time you jump a level, it's a huge increase, right? But if you look at it, now you can tell a difference between these first values here. Because you can tell, well, at 0 year, 1620, then I had somewhere between 100 and 1,000 right here. It actually probably is, like if you scale this logarithmically the whole way, it's probably not 500 because the like values in between would be scaled logarithmically instead. So 500 would actually probably be a little closer up. But definitely between 100 and 1,000, right? Less than 1,000, not many people, right? But by the year 20, right here, so that'd be 1640, we're up here. This is between 1,000 and 10,000, and it's a little higher, so this is probably closer to like 5,000 right here. And then you would keep on going out. And then so like when we get over here to 200, so that's the year 1820, we would go over here, and this is almost up to 10 to the 7th power, which would be 10,000. I mean, not 10,000, 10 million. Not quite there. It's actually supposed to be somewhere around 7 million, so that seems about right there. So, so you have to be really careful on these axes. Here, it's important to note this. With a semi-log plot where the y-axis is logarithmically scaled, exponential functions appear linear. Okay, so when you have an exponential function that's graphed regularly, if you graph it on a semi-log plot, it should look kind of like a line. And this one doesn't look very linear right here, but it looks pretty linear past like year 40 right there. So, so you can see that pattern right there. It says, use the features of the semi-log plot above to justify why an exponential model is appropriate for the population of English Americans in the current United States from 1620 to 1820. So if you were presented a question like this, you would say something like, since the data appears linear, or appears to be linear when graphed on the semi-log plot. The data shows an exponential pattern. Okay, so if the data looks linear on a semi-log plot, then it should be exponential on a regular plot for that. So if we look at the next example that he's given us, Mr. Passwater, he tells hilarious math jokes apparently. The math joke begins to spread around the school. The number of people that have heard the joke after t minutes is graphed on the semi-log plot above, where the vertical axis has been logarithmically scaled. Which of the following functions could be a model for p? Okay, so for this, it might be helpful to us. I'm going to zoom in a bunch here. It's pretty small for you guys, and you might not be able to write it in. But what's helpful to know here is for me to like draw in the values in between. So like that first point right there is at 2. And then see how those like lines get like closer together? It's like 3, 4, 5, 6, 7, 8, 9, and then it goes to 10. I know those are too little for you to see, but that's what's happening, right? So those lines are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then once you get to 10, you start counting by tens. All right, so what would this next line right here be? That's going to be 20. So that's why, Connor, I said like a point halfway between is not really 5. It's not really going to be 50 or 500. So it's like 20, 30, 40, 50, 60, 70, 80, 90, 100, right? Okay, I'm going to run out of room, so I'm not going to try to write all of that in there. So then what would the first line here be for the next one? So like right here, what would that be? It's going to be 200.
So like each time you're going up by 10, or like?
You're going up by whatever the like line before it was. So we got 200, 300, 400, and so on, right? I'm going to run out of room to write that until you get to 1,000. And then if we kept on going, it'd be 1,000, 2,000, 3,000, 4,000, 5,000 until we got to 10,000. And so that is what's happening here. So if I want to make myself like a table for the values here, then my x at that first point would be 0. My y would be 2. What would be the value for 1? 4. What about for 2? 8. At 3. Now 3 we're going to have to start guessing a little bit more. But based on the pattern I already see, 2, 4, 8, what would we have? 16, right? Which this looks about right because it is at least between 10 and 20, right? A little closer to 20. Then at 4, what should I have? 32, and that looks about right because that's close to 30, and then 5 would be 64. They don't have to. It could be like 2, 4, 8, 16. It could go up by different numbers. It's usually by tens for that. Also, notice right here, a semi-log plot doesn't have an origin. It doesn't have a 0, 0. Because it can't ever get to a 0, 0. Because if we're scaling it like this, like here I started at 1, I counted by 1, 2, 3, 4, 5. I could start at 0.1, and it'd be 0.1, 0.2, 0.3, 0.4, 0.5 till it got to 1. And then it'd go 1, 2, 3, 4, 5. So you could start at a decimal, but semi-log plots are not going to have negatives on them, and they're not going to have like the 0.00 on them, which for exponentials is fine because exponentials have that horizontal asymptote where they never actually get to 0, so it should be fine.
So they follow the same process as like a log, like they go like the, or is it like an exponential, like the x and y?
The reason, so like these points themselves look like a line, right? But the values of the points show an exponential pattern. The reason they call this like a log plot is because these are logarithmically scaled. Because like when I have log of 1, right, that would be 0 because you're saying what power would I raise this to? If I do log of like 10, that's going to be 1 because 10 to the first power would be 1. Log 100 would be 2. So, like if we took the log of what we have over here, it would be 1, 2, 3, 4, 5. That's the reason they call it a log plot. If we look at this, which ones of these graphs could we throw out? Or we could throw out A because it's linear, and while this looks linear, it's on a log plot, so it's going to be exponential, right? And we could also throw out C because if it looks linear on a log plot, it's going to be an exponential graph. So then we need to look at which one of these actually matches the values. I would just do that by plugging in a couple of numbers. So if I plug in 0 right here, I'd have 2 plus 2 to the 0 power, which would be 2 plus 1, which would give me 3. Is that right for that first point? It is not. So D must be our answer. 2 times 2 to the 0 would be 2 times 1, which would give us 2 for that. Okay here. Okay, so a note here, when we logarithmically scale the vertical axis, we're not changing the y values of the data, we're just changing the way that it's graphed. So to logarithmically scale the vertical axis, that means that equally spaced values on the y-axis are proportional, whereas equally spaced values on the x-axis are linear. So again, instead of like going up by doing 1, 2, 3, 4, 5, we are like multiplying, right? So the table above gives selected values for the values of the functions. Which of the following graphs could represent these data on where the vertical axis is logarithmically scaled? There are 2 answer choices we should throw out immediately. What answer? I mean, honestly, I'd say there's 3. Like, the answer's pretty obvious pretty soon. There's 2 of them that are not logarithmically scaled. Which graphs are not logarithmically scaled at all? Well, actually, on the y-axis. Okay, A is actually logarithmically scaled, but it's on the x-axis. That's not what we were supposed to be doing, right? C, that's just the regular graph, right? So that's those points graphed on a regular xy plane. So this actually can be a little helpful to you because it shows you sort of like an exponential pattern that you can look at. Then I've got D and B are both logarithmically scaled. Which one's going to be the correct answer? It's going to be D. I can tell it's not going to be B because B only goes up to 10, right? So I got to go up to 203. So I've got to go up, like, this is 100, so this line right here would be my 200 line. I've got to go up around 200, and that last point is there close to 200 for that. You guys see the difference between the graphs? Okay. Try 4. I want you to graph these points for me. I want you to graph those. I'm going to freeze my screen so that you can't see what I'm doing. And label each point with like the A, B, C, D. Okay, here is what I got. Look to see if your points look like they're in about the same spots as mine. There's a little, you know, like right here, that B, you definitely got to be between these two lines right here, but how high or low it is. E, you know, it's definitely got to be in between these two lines, but there's a little room to be off just a little bit for those. These are generally going to be given as multiple choice questions if they're given, so you should be able to narrow it down. Okay, questions on those? All right. Okay, so for a linear model for a semi-log plot, if you have the exponential equation y equals a times b to the x power, the corresponding linear model for the semi-log plot is given by y equals log base n of b times x plus log base n of a. And for this, n has to be greater than 0 and cannot equal 1. The slope of our linear function is log base n of b, and the y-intercept is log base n of a. The base n corresponds to the base used for scaling of the vertical axis, which is most of the time 10, but could be a different number. So what they're doing is, here you're taking your original data and you're making it into a linear equation so that you could graph it like a line instead of graphing it like an exponential. So let's just do an example. I think that's
like log as your values instead of regular numbers.
Yes, for that. So the semi-log plot above corresponds to the data table for example 3. Write an equation for the linear model for the semi-log plot in the form y equals log base n of b plus log base n of a. So we're looking back to example 3, which was this. Let me see if it'll, I'm going to screenshot this and see if it'll let me put it down here so that we can be looking at that. Let's make that smaller right there. So right there. It's hiding some of our points, but it'll be okay. A little smaller. Right here. So in this case, we're supposed to write this in the form log base n of b plus log base n of a right here. And if I look at my graph, I'm going to think about making this an exponential first if I look at my table. So if I go from 40 to 60 and then 60 to 90, what am I multiplying by? believe it is, because it's definitely not 2, right? So 40 times 1.5 would be 60. 60 times 1.5 would be 90. Half of 90 is 45. 90 plus 45 gives you 135. So 1.5 right here. I'm not going to double check, but I'm pretty sure that works out there. They probably rounded that 203. But so the number I'm multiplying by each time is 1.5. That's my B value. So I got y equals something 1.5 to the x power. And then my A value is my start value. Is that given on this table? It's not, because my start value is really like if I have a 0 right here. So to get that, I would need to divide by 1.5, right? Which would give me, it's not going to be a whole number, I don't think. Or maybe it is. No, it's 26.6 repeating. So 26.6 repeating. Now, I really did B first, right? I did y equals 26.6 repeating times 1.5 to the x power. I did part B first, which just makes more sense to me to do it that way. So if I want to write a linear equation for this, then I would need to do y equals, I'm going to do log base 10 of b, which is 1.5, right? And that is multiplied by my x, plus log base 10 of 26.6 repeating. And we can, I don't really have to write that 10 there, it's just our regular log. I'm using 10 because my axis is 10 to the 0, 10 to the first, 10 to the second. Here it's usually going to be 10, but it could possibly be something different. If I do log of 1.5, I get y equals 0.176. It keeps on going, but we'll just round it to 3 decimal places. And then if I do log of 26.6 repeating, I get 1.4259 6. Let's do 1.426. So I'm just typing those values into the calculator. Now, if I think about drawing a line right here, and I think of these not as 1, 10, 100, 1,000. If I think of this as 0, 1, 2, 3, then my y-intercept here is probably at about 1.426, right? It crosses the x-axis there. And then the slope of this graph would go up about close to 0.2 over 1. Close to 0.2, up 1. Close to 0.2, up 1. So the values here, like if I want the real equation, I need to use this one. But if I want to see the like linear equation for this graph, if I count this as 0, 1, 2, 3, this is what I would do here for that.
Could you leave it in log form, or do you have to solve it out?
I think it just depends on how, like, what they're asking you and how they leave it for the problem for that. I don't think it's going to be the bulk of, like, what you have to do on these here. Okay. Questions? All right. So